I'm Grace Garmeyer.
And I'm Trevor Lowe.
And this is M.E.G.A.N.
Go for it.
M.E.G.A.N is a two-wheeled self-balancing robot controlled by a Lego EV3 unit. We use this button to set M.E.G.A.N's balanced angle, and this gyroscope measures the angle offset from this balance point. The gyroscope angle is supplied to the EV3 unit, which then supplies power to the motors corresponding to the angle offset so that M.E.G.A.N can be self-balancing. M.E.G.A.N also has a distance sensor, so she knows when she is nearing an object.
So our code is overall run using this big loop here, which is a while loop that will continuously run our controller here. So our controller setup is a PID controller, so a proportional, integral, and derivative term, and it all starts with measuring the gyroscope angle, which then has the gyroscope offset angle subtracted, and more on how that's come up with later, and it is multiplied by our proportional gain, which is minus 29 right now, and that gives us our proportional term, which is then added with the other two terms. The second term, which is the integral term, is calculated using a shift register, which will repeatedly loop around the value for the integral, so it can add the value of the angle multiplied by 0.007 each time, loop it around, and then goes into that shift register right there, and then its sum total will be multiplied by our integral gain, which is minus 8 right there, and then it will go also into that integral term scope that you see. And that term is added along with the proportional term. The third term would be the derivative term, and that term is also done using a shift register, where it takes the current value of the angle and subtracts the previous value, and it gets that previous value by using a shift register on the angle measured from the gyroscope you see right here. And then once that difference is calculated, it is multiplied by a derivative term, or derivative gain, which is minus 21, and that will go into our derivative term scope and is also added along with the other two terms. Finally, the angle of the gyroscope is also output into a scope, and the sum of those three terms are outputted into the control signal, which then tells the two motors in ports 1 and 2 how much power to output. The entire loop is controlled using the outputs of a distance sensor, which is the ultrasonic sensor, and it basically just says if the distance to a nearby object is less than 10 centimeters, then it will stop the loop. And that's all there is to it.
The biggest problem we're facing with our robot is drift induced by the gyroscope. So we incorporated this button to reset the gyroscope. But if we press the button while holding the robot, even if the robot wiggles just a tiny bit, we get a good amount of drift in our gyroscope, as demonstrated by this plot. To fix this issue, we implemented a gyro reset into our code so that the robot can be completely still when we reset it. As you can see now, we have no more drift in our gyroscope.
So that button was implemented in code using this loop right here, and this loop runs before the rest of the code, as you can see, and the way it works is it will read the angle for the gyroscope, it will then wait 10 milliseconds and then read the rate for the gyroscope, and if that rate is equal to 0, it will stop the loop, moving along the code to reset the gyroscope in port 1 and then go on with the rest of the code. This allows us to only reset the gyroscope when the robot knows that it's not moving.
Okay. As you can see, when Megan's in a balanced position, the gyroscope angle is not 0. Instead of trying to hard code this angle offset into our code, we implemented this button, which when pressed will reset the offset angle. So we can just press the button when Megan is in the balanced position.
So the way that this was implemented in code is using these two blocks right here. And so the first block simply just waits for the button in port 3 to be pressed, and then the second block reads the gyroscope in port 1 and takes that angle that is output and sends it into the loop, which will be the constant offset used whenever the loop is reading the gyroscope angle. It's important to note here that the gyroscope reset is only done when the robot knows that it is not moving. We couldn't have the robot reset the gyro whenever we push the button, because usually when we push the button, the robot is actually moving, which would have induced drift like we talked about earlier.
Now let's see Megan in action. As Megan tilts, the proportional term, the integral term, and the derivative term all change with her movement and add together to form the control signal as seen here on the screen. As seen here, Megan's motors turn off when her distance sensor senses something in front of her. The distance sensor doesn't always respond quickly since it is contained within the same loop as the rest of the code. Megan does have some limitations. Once she falls forward and her gyroscope is bumped, she will no longer be able to balance. We lowered Megan's EV3 unit to be as low as possible to the ground to counteract the weight of her large motors on the back, so that Megan would have a lower center of mass, leading to a lower moment of inertia. And we did this so that Megan would be able to balance better. Because Megan only has connection spots on the side and on the back, it constrains where we can put the EV3 unit and the motors, which makes it difficult to adjust the center of mass and moment of inertia in the ways that we would like. Megan also cannot be unplugged from the computer.
When we target the code to the robot, right here, this is the same code as before, and then unplug it and try to run it, it has some problems. The motors don't seem to actuate as well, and code generally does not seem to read the gyroscope very well. To try to solve this issue, we tried several things, including implementing a delay, ensuring that the battery life was adequate, and actuating both motors together rather than separately, and none of them seemed to solve the issue. It seems to be an issue with the EV3 that we can't fix.